And thank you all for the opportunity to speak to you today. To motivate this talk, I'll open with the question, what are robots good for? Obviously, they're pretty good at welding cars. This is a classic example of where automation has really exceeded the capabilities of humans. Nowadays, they're getting pretty good at driving cars also, although maybe not. Clearly, there's still some challenges here. But I've never seen a robot vacuum the inside of a car. So is vacuuming the inside of a car that different from welding one? In fact, there's one important difference. The factory presents a highly controlled environment where every car needs exactly the same weld in exactly the same places. At the car wash, though, rote repetition won't work, and an intelligent system is required to sense and react to changes in the environment. So to make the move from automation to autonomy, a robot needs to be able to sense and make sense of its environment. This is what we call spatial AI. The spatial piece is knowing where things are, knowing the geometry of the scene, and the AI piece is knowing what things are, the semantics. We also want to keep track of things as they move or as the robot moves. I would, of course, be remiss to omit deep learning. Deep learning has been a real paradigm shift in artificial intelligence, and barriers to entry for using deep learning have fallen. There are open source networks built to tackle all kinds of problems, and it's not onerous to retrain them. You can start with a pre-trained network and refine it on custom data in order to solve your own particular problem. So what I want to discuss is how can we use this progress to advance manipulation? Well, the first piece comes from the theory of image formation from classical computer vision. A neural network can find which pixels correspond to an object, but a robot can't grasp pixels. A camera calibration, along with depth sensing, lets us place the information from the pixels into the world. We can unproject the pixels back into 3D space. There are open source packages available for intrinsic and extrinsic camera calibration. Intrinsic calibration determines the parameters like focal length and lens distortion. In the example that Ramon just gave, where the scale of the bin was incorrect, that kind of error could occur from a poor intrinsic calibration. The intrinsic calibration is the camera's pose relative to the robot, and that could be a rigidly mounted robot or rigidly mounted camera in the scene, or a wrist-mounted camera. OpenCV and other open source tools exist for intrinsic calibration. MoveIt calibration is an open source package maintained by PickNik for extrinsic calibration. So while 3D perception is feasible with a monocular camera, an RGBD camera or LiDAR can save a lot of complexity and computation and generate more accurate data. The camera calibration is the first essential step to use the information from an image in order to interact with the real world. Once you have a calibration, the next piece is object localization. Again, using an RGBD camera makes localization a lot easier, but we still need some way to combine information from many pixels. If your object of interest has a fixed known shape, for instance, if you're picking up molded parts, the observed point cloud can be matched to a CAD model. However, we don't always know the exact shape. In an agricultural application, you might be picking fruit, and no two apples are exactly the same shape. So in this situation, it's common to use a neural network to segment the object, and then the centroid or bounding box center of that point cloud is usually sufficient for determining where the object is in the scene. Here are two open source libraries for 3D perception that can be used to tackle this kind of problem. PCL, or the Point Cloud Library, and Open3D. We're not quite done yet, though, because it's insufficient to find an object just once. If the object or the robot is moving, we need to track it across multiple frames. This is another application of pretty classic computer vision. Using a filter such as a Kalman filter or one of its variants, we can update our belief about where the object is as each new frame arrives. Here we have a red oval representing the distribution of where we think the object is currently here at the red cross, based on when we last saw it and how fast it was moving then and all of that. Then we have a new observation coming from our image. Our object detector says, oh no, it's actually over here at the blue cross. And so we update our belief about where the object is by combining those two pieces of information to get a new guess. And this is, again, an algorithm that's available in OpenCV. But next I want to talk about some problems beyond bin picking and pick and place. There are many other challenges in manipulation, and many of these come with unique perception demands also. For instance, rastering over a surface, especially, we need to maintain contact with a surface and maybe apply a specific amount of force. Another class of problems would be interacting with semi-fixed objects. So now it's not simply sufficient to have a grasp and then move through free space in order to then move to a placement pose. We need to open a door, turn a screw, insert a plug, and these are all motions that have constrained or limited degrees of freedom. And finally, interacting with non-rigid objects is a very general and very challenging class of problems. And these are all very hard problems, but they're becoming increasingly feasible. At PickNik, we've worked with companies to attack many of these problems. So I'll go into discussing them a little bit more. One common piece for a lot of these is on the motion planning side, they demand a reactive, real-time planning, local planning system. Move It Servo is one such system. It's part of the Move It package that's maintained by PickNik. And what this means is we can't just compute a motion and say go. We need the planner to adjust the plan in reaction to sensor input. We can use some of the same vision tools I've described earlier, but because we need this real-time reactivity, performance becomes much more important. I'll dig into these problems a bit more. First, for rastering over a surface, I'll go back to this example of vacuuming a car seat. The perception to this problem, the perception pieces to this problem are first merging several views into a single cloud, which is known as point cloud registration. Then second, combining those points into a mesh to define a surface. And finally, segmenting the area that we want to vacuum. So we don't want the vacuum to go over the edge of the seat, down to the floor, across the floor, out the door, down the tire, and then vacuum the whole world. So we need the perception system to define what the boundary is for the work surface. This segmented surface then can be passed to a global planner that might come up with a general trajectory like this. The local planner, which is what I was describing earlier, is then responsible for executing that trajectory, keeping the end effector close to the path, in contact with the seat through the whole motion. Next, another modern motion planning tool that we've used at PickNik is affordance templates for interacting with semi-fixed objects. An affordance template is a combination of a geometric model, which is the template for an object, and an affordance, which is an action or some way of interacting with the object. There's an example on the right here taken from the DARPA Robotics Challenge. At the top is a point cloud that the robot has sensed, and the white ring that you see there is the template that represents the valve that the robot can turn. Once the perception system has matched that template to the observation, the motion planner can adapt a pre-planned motion to the observed location of the valve. Just as before, shape matching can be used to place an affordance template, while deep learning is useful for making more general templates, such as a generic door handle. Lastly, I'll briefly mention some challenges with non-rigid objects. Typically, physical models for non-rigid objects are inaccurate or expensive to compute, or both. And there's current research into substituting those expensive models with cheaper learned models that have been learned using deep learning, that are cheaper to compute. Non-rigid objects also pose some perception challenges. In particular, liquids often have a reflective surface, which can be especially hard for active sensors such as LiDAR or RGBD cameras using infrared emitters. One strategy here is to segment the liquid surface in the RGB image and then use the boundary just outside that segment in the point cloud to determine the position of the surface. Another task here is to measure volume using 3D perception and a scene model. So some of these problems are solvable now, especially in more controlled environments, while others are more questions of open research. To quickly summarize, I've spoke about spatial AI, which is useful for identifying, localizing, and tracking objects. Real-time local planning is often a key piece for manipulation tasks beyond pick and place, and also that it's very useful too for picking moving objects. And then classic computer vision still really has a significant role to play in robotics and automation, and determining the scene geometry and placing the information from a deep learning output maybe into the scene. And of course, deep learning there provides the scene semantics, and it really drives more of the higher level global planning and decision making. So thank you very much for your time, and I look forward to your questions at the end of the session.